Hello and greetings. My name is Jesse Hammer, and today we're going to discuss the dominated convergence theorem, or DCT. Now, the DCT is a complicated measure-theoretic proof I don't feel comfortable covering, but I can give the essential statement of the result as it pertains to calculus BC. The conditions are that we have a class of functions f sub n that tend to some particular function f on an interval a, b. And second, that there exists a function g such that the following set of conditions hold. Specifically, the absolute value of g is greater than or equal to the absolute value of f sub n for all n and x on the interval a, b. We also have to have that the integral from a to b of g does not diverge. It is a finite integral. Then we have the result that the integral from a to b of the sum of f sub n dx is equal to the sum of the integral from a to b of f sub n dx. Now, these conditions are important because if they're not met, this nice result doesn't necessarily hold. For example, in the case where e to the 2x dominates e to the x on 0 to infinity, but the integral from 0 to infinity of e to the 2x dx diverges. So this result doesn't necessarily hold. So in order to see an example of the utility of the DCT, today we're going to evaluate the integral of cosine of x from 0 to pi over 2 using power series. So then we can integrate both sides of this equation from 0 to pi over 2 with respect to dx. And now we can make use of the DCT, noting that -1 to the n over 2n factorial times x to the 2n is less than or equal to 1 on the interval 0 to pi over 2 for all n. So g of x equals 1 actually fulfills our conditions. So then we can do what the DCT allows us to do and swap sum and integral, giving us this expression here. Now we can remove the -1 to the n over 2n factorial from the integral, as that's just a constant with regards to dx. And we end up with this expression here. At this point, we can just integrate x to the 2n in general, and we end up with this expression, x to the 2n plus 1 over 2n plus 1, evaluated at the endpoints, pi over 2 and 0. So this denominator here, 2n factorial times x to the 2n times 2n plus 1, we can just pull together into 1 factorial, 2n plus 1 factorial. So this power series you might recognize as the power series for sine of x, evaluated at the endpoints pi over 2 and 0. So if we have sine of x evaluated at pi over 2 and 0, we could just plug in the endpoints. We end up with sine of pi over 2 minus sine of 0, which is 1 minus 0, and then our answer is 1. And there we're done.